Hello, and welcome back to a video series on MAC 1105 College Algebra. My name's Sean Perry. These are guided notes number 3 in the series on section 2.3, complex numbers. We should probably begin with a review on what a complex number is. We know that we need two numbers to come up with a solution to this equation, because both -1 and +1 squared will give me 1. And because a negative times a negative is also a positive, and positive times positive is of course a positive, there really doesn't seem to be an answer in the real numbers to this equation where I put a negative sign in front of the 1. So what we do is we create a solution to this equation. We say we're going to define a number I that is a constant value to be the principal square root of -1. And this entails the property that if we square such a number, it will give me -1. And what we'll do is simply use I as if it were a variable when it comes to combining like terms or things of that kind. But when we have to square it or take higher powers of it, we can rely on this property that reduces those squares to the number -1. That's pretty much all there is. A complex number then is sort of a compound of two numbers, A and B, who are real numbers, and we call this number A the real part of the complex number, and we call this number B the imaginary part of the complex number. So it should be noted that if B is 0, then we just get a real number. So real numbers are a kind of complex number. And if A was 0, we would just have BI. We call that a pure imaginary number. So now let's jump into doing some arithmetic with things of this kind, just using the ideas of like terms, because that's all we need to do addition and subtraction of complex numbers. So here I've dropped the parentheses because they were more or less just organizational parentheses showing me one and another complex number. And if we rearrange things, we can now sort of get things with an I together and things without an I, regular old real numbers, together, and add those up to give me 32. And here, I mean, let's remember that if I is functioning just like a stand-in for any constant, then it could be factored out. And so we could use like terms to just combine the 8 and the -10 together to give me -2i. Now, it should be noted that in general, if we have two complex numbers, a plus bi, and another number, c plus di, really all I've done here to accomplish this addition is to add up the real parts and add up the imaginary parts, taking into account that sometimes when I have a negative number, we might have to be looking at our sign rules for addition of negative numbers here, but that's really all there is to it. It's not so very much trickier to do subtraction, but now I would say these parentheses are a little bit more than organizational. We have to remember to distribute this minus sign against each of these terms. We're subtracting the whole thing, so we need to subtract each term. This would instead give me 13 minus 19 for the real parts, and we would have -10i minus 8i for the imaginary parts. Combining those again with like terms would give us -6 minus 18i. And just as before, there is a sense in which if we wanted a formula here, if I had a plus bi and I subtracted from that c plus di, really all I'm doing is taking the difference of the real parts and the difference of the imaginary parts. These two, addition and subtraction, have pretty simple formulas that you can sort of use instead of having to work out, all the like term stuff and have a rearrangement step. Okay, those are the ideas. Let's practice. Here I have 18 minus 15 and minus 22i minus 13i. Combining like with like, we get 3 minus 35i. With the difference, as before, we need to remember that we are distributing, just as we did up here. We need to make sure that the negative sign attaches to both of these and changes their sign appropriately, which would give us 18 plus 15 for my real part, and then minus 22i plus 13i for my imaginary part. So what are those? Looks like 33 for my real part, minus 22 plus 13. That's going to give me minus 9i for my imaginary part. 3 and 4 aren't so very much different. They are, in fact, a bit simpler. we just have to simplify the radicals first. Let's even just say, for simplicity, that this c is a positive number. This is no different than the square root of c times -1. That's what a minus sign means, after all, is times -1. And so this will be the square root of c times the square root of -1. But by definition, we said that that is going to be I. So you can see the difference between minus c. So you can see the difference between the square root of minus c and the square root. So you can compare the square root of minus c to what we have on this side. We have just the square root of positive c, and I has been pulled out of the equation. So remember, if you want to get rid of a minus sign under a radical, just pull its I out. So this one over here, minus 36, well, the square root of 36 is 6, and the square root of a negative is I. There's still a times -1 up front, which is the same as making it negative. Here I have minus 9I under my square root. The square root of 9 is 3, and the square root of -1 is I. And they still want us to take that and multiply it by a -4. So we carry that out. Minus 6I minus 4 times 3 is going to be -12. Multiplication's associative, so we can do this part first. And that's minus 12I, of course. And now combining like terms, we get minus 18I. Here things are a little bit different because this radical does not completely simplify. 360 is 36 times 10. And so if I take the square root of 360, it's the square root of 36 times the square root of 10. Now, the I is going to come out because of this minus sign, but all that the 360 is going to simplify to is going to be 6 radical 10. So combining those two ideas, the I and the simplification of a radical, we have the following. Minus 4 times 6 radical 10 I plus 4 times 6 radical 10 I. But wait a minute, hang on just a second. This is minus 4 of something plus 4 of something. It doesn't matter what that something is, 24 square roots of 10I. But we're taking something and adding it to its negative. That's 0. This is a silly question. Let's move on. The following questions have to do with the multiplication of complex numbers. The main idea here being that we're going to follow all the usual rules. Associativity, commutativity, distributivity, all of these apply. The only difference is we're going to want to include our little notion that I squared is equal to -1. So what I mean by that, to show too much work, is that this could be rewritten. This is just -4 times I times 11 times I again. And there's no reason to keep it in this order or to continue to think about it in this order. We could write -4 times 11 times I, which is I squared. Now, -4 times 11 is -44, but I squared is -1. And so that's going to turn this back to a positive 44. With this one, we really are just multiplying by the number 2I against the sum in parentheses. And when we multiply something against a sum, we need to distribute it against each term in the sum. So in the first case, that would give me 2I times 6 plus 2I times 9. But regrouping things a little here, that's 12I and 18I. These are like terms in terms of I, and adding them together, we get 30I. Here we have another one, but we are distributing a 3 against both terms. This is going to give me 27 plus 18I. There's no way to continue to reduce this because the i's and the not i's are not really like terms. So we just leave it like this as the end result. As long as your number is in the form a plus bi, we can count this as an answer, a complex valued answer. Finally, to square away real, general, complex multiplication of two complex numbers, a plus bi and c plus di, we're going to just want to follow our foiling rules. Remember that foiling was just distributing twice. It really is just a distributive property applied twice. Once to one parentheses to get it into each one of these things, and then again to get each one of those things back into the parentheses. This makes sure that we hit all 4 possible options. So it's more customary than applying the distributive property twice to simply look at all 4 of those possible combinations: first, outer, inner, and last. So the first one is going to give me 50. The outer ones is going to give me -6 times 5, that's -30i. The inner one is minus I times 10, that's minus 10I. And the last one is minus times minus, that's a plus, I times 6I, that's 6I and they're squared because there's two i's. Now, as before, the I squareds cancel to minus 1, or I should say the I squareds reduce to minus 1, which means that actually this last number isn't in terms of I, it's just going to be a regular number. It's going to be minus 6. So we really do wind up with 50 minus 6 minus 30i minus 10i. And now combining like terms as before, we get 44 minus 40i. We do complex multiplication so often that it's probably worth looking at it in general. If I have a plus bi and I multiply that by another number, c plus di, I'll get a times c, and then my last terms are going to be bi times di, which gives me bdi squared, which is minus bd, another real number. Let's put those up front, and then on the inside part, we're going to have a di plus b ci. So factoring out the I, that's AD plus BC, I. I wouldn't recommend memorizing this equation. It's a bit. I mean, it's not the worst, but there's a lot going on there. Instead, what I would memorize is the process that you use to get that equation. What you're doing is foiling, and you're not doing anything else other than foiling, and taking advantage of the fact that I squared was equal to minus 1. There's nothing else going on. If you can do those two things, then you don't really need this formula. You can produce it at will. All right, so let's apply that procedure to the following problems. Here we actually have a very interesting set of numbers, because you'll notice that the numbers are nearly the same. The only difference is that the middle sign, the sign that's attached to the imaginary part, has changed. And you might compare this to the difference of squares formula. If I have a minus b and I multiply that by a plus b, well, something pretty interesting happens, right? Because you have a squared, and then you have a minus ba and a plus ba that cancel as middle terms. And the only thing that's really left is minus b times b, which is minus b squared. Now, the idea is that for complex numbers, this situation is even better, because for complex numbers, this b would have an I next to it. And so this would be I squared here. And that, of course, cancels to minus 1, which changes this to a positive. So what we wind up with in the end is just a real number, a squared plus b squared. That's pretty cool, because we went from having a complex number, we multiplied it by another complex number and got a real number back. So that is so important that we want to call these two companion numbers by some special name. We call them conjugates. And we say that the complex conjugate of a plus bi is a minus bi. Just not changing the sign of a, not negating it, but just changing the sign of the imaginary part. So let's see how that looks in this problem. When I multiply minus 6 together, I get 36. Minus 6 times minus 6 is 36. And then these two inner parts, minus 4 times minus 6, positive 4 times minus 6, that would give me plus and minus 24 respectively. The i's don't really matter here. I'm going to have 24i and minus 24i. Those are going to cancel. And the last terms are going to be minus 4 times minus 4. That's minus 16. But then we also have an I squared. And the I squared is going to cancel the minus 1, which turns this into a plus. And that gives me 52, the real number 52. Now, something different happens when we square. Let's rewrite squaring as times itself. So no change in the sign here. And then let's apply our foiling thought process. I want the first terms, minus 14 times minus 14. That's going to give me 196. Then let's do my last, because we've already seen how this is going to be another real number. That's minus 3 times minus 3. That's plus 9. But then times I squared, which gives me minus 9. Now let's do our middle terms. Let's take these inner terms here. Let's say minus 3 times minus 14. That's going to give me 42. So we'll have plus 42i. And likewise, this one is the same. This is another plus 42i. And so combining my like terms all together, we wind up with 187 plus 42i. So squaring it did not turn it to a real number. Multiplying by a conjugate would do that. Here's something a bit more general. Let's rewrite it in terms of complex values first, right? We have 11 plus the square root of 144 is 12, and the square root of a negative is I. Likewise here we have 5 plus 4I. Foiling now, we're going to have 55. We have 12 times 4, that's going to be 48, but we have I times I, making it negative. Then we have 60I, and we have 44I. Subtracting these two gives me 7, and adding these two up gives me 104I. The following problems have to do with complex division, and complex division is going to be a little bit different than all the things which have come before. What's come before has required no real tricks. All we had to do is follow our nose as far as the distributive property or like terms were concerned. Complex division is a little different in that we have to know a trick in order to do it, but the trick isn't too bad. The trick, in fact, involves the complex conjugate, because you see, if I have a sum or a difference in the denominator, I can't simplify it, and neither can I turn this into one number because it's not like terms. But we've just seen a trick about what I can multiply by in order to turn a complex number into a single real number, and that's multiply it by its conjugate. Now, of course, we can't go around multiplying things by their conjugates wherever we like, unless, of course, we also do it in the numerator as well as the denominator, because then I've really just multiplied by 1. Complex numbers or not, a number divided by itself is still 1, and 1 times anything is still itself. Now, this requires 2 complex multiplications in order to pull off. What's going to happen on the bottom, though, is pretty nice, because on the bottom, we have a number times its conjugate. So we'll have 2 times 2 is 4, minus 3 times positive 3 is minus 9, but then times I squared gives me plus 9. And on the top, we actually have to FOIL this sucker out. We have minus 2 for the first. For the last terms, we have minus 18 times positive 3. That's going to give me 54, negative 54, but positive once we change it because of the I squared. Then we've got the inner term. Negative 18 times 2 is going to give me minus 36, and that's minus 36I. And then our outer terms, minus 1 times the 3I, gives me minus 3I. Let's simplify this a little bit. We get 13 on the bottom, we get 52 for the real part of the top, and then we get minus 39 for the imaginary part of the top. Now, it just so happens that 13 divides these, but even if it didn't, what I would do is I would write this as 52 over 13 minus 39 over 13 times I. That's because now we have it in the form a plus bi, where a and b are these real numbers, 52 over 13 and minus 39 over 13. That's how we get our division to be a single complex value instead of some combination of complex values. Now, in this case, we have some simplification that goes on. 13 goes into 52 4 times, and it goes into 39 3 times. So we have this nice simplification. For this next one, you could do the exact same thing. We could multiply by the complex conjugate, but the complex conjugate of a pure imaginary is another pure imaginary. And in this case, you could already see the complex numbers are going to cancel in some way. In fact, there's already a lot of reduction in some way. Really, all we're doing is multiplying on the top and bottom then by I. This is sort of a special thing for pure imaginaries. If you want to just remember the one trick, multiply by the conjugate of the denominator on the top and bottom, you can do so. What do we get on top? Minus 2i. What do we get on the bottom? 7i times I, which is 7i squared, or minus 7. And a negative divided into a negative gives me a positive, so we could rewrite this as 2/7 times I. And that would be my final answer. Now, let's go on. Here we have, again, something a bit more general. For a denominator, we have 2 minus 5i. We're going to want to multiply that by 2 plus 5i on the top and the bottom, because if we do so, we wind up on the bottom with 4 for the 2 times 2. Minus 5 times plus 5 is minus 25, but then this is I squared, so this turns into a plus 25. And on the top, we wind up with minus 2i, and then minus 5i squared, distributing this I against both these top parts. but there's some reductions that can be done here. I squared is minus 1, so this is just positive 5, minus 2i, and on the bottom we have 29. Now, there's no way to reduce this nicely, but we do still want to write it as 5 over 29 minus 2 over 29i to get things into our a plus bi form. Let's take this one, do the same trick, 6 plus I. Instead, we want to multiply top and bottom by 6 minus I. On the top, that's going to give me negative 36 plus 6i. And in the denominator, we have 36 minus 1 times positive 1 is minus 1, but then I squared is minus 1, so we have plus 1 here. And this is going to give me minus 36 over 37 plus 6 over 37i when I distribute. This problem, we are again dividing by a pure imaginary, so it suffices to just multiply by I over I. Minus 3i over minus 3i is fine, but the minus 3's immediately cancel, and we just get this. On the bottom, that would give me minus 3. On the top, that would give me minus 5i minus 3i squared, distributing the I again to both terms. And rewriting this as plus 3 minus 5i over minus 3, we divide each term, and we could actually reduce one of them. Let's say this is minus 1 plus 5/3 I. 17 really is no different. We just have to write it as a complex number right now. This is minus 7 over minus 3 minus square root of minus 10. Well, that last part is just minus radical 10i. And you might think to yourself, oh, well, there's a square root of 10 in there. Surely that will cause problems. But actually it doesn't. One of the main ways we could deal with all of that malarkey is we could, deal with a radical like this in a denominator is to multiply by a conjugate as well. If you have a denominator that looks like square root of a plus the square root of b, you could actually multiply this by the square root of a minus the square root of b on the top and bottom. Notice the form of a conjugate here to square both terms without really messing up the bottom. And that would get your sum out of the bottom of the denominator, which is way better. That's a little bit of a digression. Let's talk about signs. I can't help but notice there's a minus sign out front and all these negatives here. That's a pain in the butt, so let's get rid of a few of these negatives right off the bat. Putting a minus sign out front is no different than saying this whole thing is times minus 1. Or you could instead think of this as attached to the numerator. But the denominator also has a minus 1 that's sort of distributed to both of these terms. So what I could do is factor that out and cancel to give me 7 over 3 plus square root of 10i. And that's just going to make there be a few less negatives to carry around to see what we're doing. What we are doing is multiplying by the conjugate of the bottom, which is this, changing the sign. And we want to do that on the top and bottom. And let's see how that improves our life a little bit. On the top, we're going to have 21 minus 7 square roots of 10 times I. And on the bottom, we're going to have 3 times 3, which is 9. We're going to have the crossing terms, which cancel. And then we're going to have square root of 10 times the square root of 10, which is 10. And the I squareds will make that a plus 10 instead of a minus 10. This gives me a 19 on the bottom, which isn't too big a deal. We'll have 21 over 19 minus 7 radical 10 over 19 times I. And notice that even though we had a radical on the top still, because we had a single number in the denominator, I was able to split it up like this and write things in our a plus bi form as desired. Okay, that does it for this video. Thank you very much for your patience. Have a great day. Good luck with your studies, and I'll see you in the next one.